Welcome to the Explainer. Today, we're jumping right into what I like to call the ultimate systems programming showdown. In systems engineering and software architecture, performance is absolutely king. You need speed, you need efficiency, and of course, reliability. But picking the foundation for a major project, well, that inevitably forces a pretty massive choice on you. Okay, let's dive into this. We're looking at a classic tension today, a real heavyweight battle between raw hardware-level speed and the incredibly urgent, modern need for memory safety. Both Rust and C have staked a major claim to the throne in this space. But, which one actually delivers the performance developers need without causing catastrophic failures down the line? That is exactly what this explainer is going to answer. So, here's the tale of the tape for today's agenda. First up, the legacy of C. Second, the cost of speed. Third, Rust's modern approach. And finally, number 4, the final verdict.
All right, kicking things off with Section 1, the legacy of C, the reigning champion.
We really can't talk about systems programming without paying some serious respect to the reigning champ here. To understand C's massive dominance, just take a look at this timeline. It began all the way back in the early 1970s, which means C is over half a century old. It was developed specifically to rewrite the Unix operating system. Then, moving into the 1990s, we saw the development of this vast, sprawling ecosystem of libraries and tools. And here we are in 2026, and it continues to be the trusted standard for embedded systems. I mean, a track record like that is frankly hard to argue with. Now, what's really interesting about this slide is exactly what gives C its performance edge. Why is it just so incredibly fast? Well, it basically comes down to direct hardware access. C allows programmers to write low-level code that interacts directly with the computer's actual hardware. You get this precise, surgical control over system resources for fine-tuned optimizations, and that's paired with code portability across various platforms without really needing significant modifications. And that brings us to a phrase you hear constantly in this space: software that lives close to the metal. Because C has minimal runtime overhead, it executes incredibly fast. It's basically talking almost directly to the machine itself. But, as we'll see, living this close to the metal, well, it definitely has its dangers. Which brings us to Section 2, the cost of speed and its safety limitations. This right here is the core tension of our explainer. We've seen C's raw power, right? But every superhero has an Achilles heel. Because C gives developers such precise, unrestricted control, step 1 is that it inherently lacks built-in safety features. The compiler essentially just assumes the programmer is completely flawless, which, let's be real, we rarely are. And that leads directly to step 2, common human errors like buffer overflows and undefined behavior. Then, those mistakes just snowball into step 3, which is severe system vulnerabilities and catastrophic crashes. It makes it kind of tough for modern, highly robust applications. So let's look at Section 3, Rust's modern approach to performance and safety. This completely opens the door for a modern challenger promising the holy grail of systems programming, the raw performance of C, but entirely eliminating those crash-inducing pitfalls. So the crucial point is this concept of zero-cost abstractions. Rust's design philosophy enforces safety at compile time, but incredibly, it does it with absolutely zero runtime penalty. Unlike other languages that have to use a heavy garbage collector to clean up memory as it runs, Rust handles its abstractions before the program even runs. The safety guardrails are just built right into the structure of the code itself. To actually pull this off, Rust relies on 3 core concepts, and it does have a bit of a steeper learning curve, starting with ownership. This is Rust's strict compile time rules system. It basically guarantees memory safety without needing a garbage collector by ensuring that every single piece of data has one and only one owner at any given time. And when that owner goes out of scope, boom, the memory is instantly and safely freed. It's a completely different way of thinking about memory, but man, it yields immense reliability. Let's move to the next slide and see how this builds directly into the second concept, borrowing. Remember those nasty system vulnerabilities we talked about in C, like null pointer dereferencing? Borrowing stops that dead in its tracks. It's a clever mechanism allowing safe access to data without actually taking over ownership. You can borrow the data to read it or modify it, but Rust's strict rules guarantee you can never accidentally destroy it or try to access it after it's already gone. And the final piece of the puzzle here is lifetimes. These are strict checks ensuring memory references remain valid only for as long as they are actually needed. But honestly, what is truly amazing about all of this is Rust's compiler itself.
If you mess up and violate ownership, borrowing, or lifetimes, the program simply won't compile. No way. Instead, it gives you incredibly detailed, helpful error messages. It's kind of like having a strict but totally brilliant mentor looking over your shoulder, reviewing every single line of your code to guide you to safety before it ever even runs.
All right, it is time for Section 4, the final verdict, choosing your champion.
Let's bring both of these heavyweights back into the ring for our final head-to-head analysis. And this brilliantly illustrates the core choice every systems developer faces today. Over on one side, you have C offering direct hardware access and generally faster raw speed. And directly contrasting that on the other side is Rust, offering guaranteed memory safety and simplified concurrency, which just makes it so much easier to write multitasking programs without the whole thing crashing down. When we look at this table and weigh the trade-offs, the distinctions become super clear. Under speed, C is generally faster for raw tasks, but Rust keeps pace right there with its zero-cost abstractions. For safety, C remains vulnerable to overflows, while Rust enforces strict memory safety. And when we talk about the learning curve, C is proven, ubiquitous, and accessible. Rust, it undeniably has a steeper curve because of all those compiler checks we mentioned. So essentially, you're trading a bit of upfront development ease for unparalleled long-term reliability.
I want to highlight a fantastic quote from our source material author, Nora Fitzgerald. Drawing from her real-world background as a systems programmer writing OS internals, she states, "Correctness and performance are the same requirement." And I think that's our ultimate unified takeaway here. It really doesn't matter how screaming fast your program runs if a simple buffer overflow leaves it wide open to a massive exploit. True performance means operating correctly, even under immense pressure.
So I leave you with this provocative thought to ponder: speed or safety? Which trade-off is going to drive your next big systems project? Are you going to lean on the proven raw speed of C? Or will you embrace the strict compiler of Rust to guarantee that sweet memory safety? The battle is definitely ongoing, but armed with this knowledge, you are officially ready to choose your champion. Thanks so much for joining me on this explainer, and keep learning.